Welcome back. Welcome back. So we'll just continue our discussion from last part. In the last part, we looked at how we can use linear regression to solve an inverse problem. In this part, we will look at an important quantity called the goodness of fit. What the goodness of fit determines is how good the regression fit we got was. So what this determines is how good the fit we proposed is. So in the last video, we had seen the example of a linear model with the data that was given here in this inverse problem. And we had obtained both W0 and W1, the coefficients of the linear model, and these were the values that we obtained. Now, once we obtained these values, once we plotted them, remember this was the best fit that we had obtained, this red line. And the data is sort of scattered around this best fit line. So again, the question really is, how good is the best fit line? Now, why do we ask this question? Suppose somebody says that it is not a line which is the best fit, but let's say a quadratic curve, which is the best fit. How do you compare these two different proposals for the hypothesis function, proposals for the function which actually fits the data? Now, in this particular case, we had already used a linear fit because we said theory predicts that. But suppose somebody has a new theory. They say, no, the theory that you used, which was that d by dx of k dt dx is 0 is wrong, and here is experimental evidence of that. Then we needed a comparison between essentially noisy data fits like our best fit line and some other fit, and we need to compare two different theories. So this is useful in comparing two different fits. Okay, so here is an idea. We'll start with the preliminary proposal, so which I'll call proposal 1. This is not quite accurate, but it will give us an idea of how to proceed to determine goodness of fit. So the idea is very simple. We look at how good this fit is by finding out the error. So I say, okay, we already have a measure for our error. So we have S equal to sigma of yi minus, remember, y hat I is essentially our fit. We square this and we find this out. And this is a measure of goodness of fit. We sum this over all data points. So this is our proposal. Remember, this is not quite accurate for reasons that I will tell you. And we say that if S is high or large, then this means it's a bad fit. And if S is small, then this is a good fit. Okay. So this is my proposal. This is our proposal on what a possible measure of goodness of fit is. So it turns out that this has two problems. Okay, so this entire proposal has two problems. So those problems are as follows. Firstly, okay, high or low with respect to what? So this is a general lesson in science and engineering. One cannot talk about something being high or low without saying with respect to what. So there has to be a non-dimensionalization or some comparison. For example, if I measure the temperature, here I have measured it in degree centigrade. Suppose I measure it in Kelvin, it might look that, well, in this case, it won't be Kelvin, but suppose I measure it in Fahrenheit, it might look like the temperature gap is high. Okay. If this distance is measured in millimeter versus this distance is measurement in kilometer, these are just numbers. So will I say the distance of 1 is high or what? You will say 1 watt, 1 kilometer, 1 meter, 1 millimeter, and depends on the physical context. So without context, without some comparative number, okay, so we need some base of comparison. And without that, we can't really say. Now, the second problem is related to the first problem. Okay. So we would like a quantitative measure, absolute measure of goodness. Okay. So like I said, it's related. For example, good equal to 1. I mean, on a scale of 0 to 1 or a scale of 0 to 10, we are going to choose 0 to 1, and we can say that bad is 0. Okay, so these two problems turn out to be related, and if we use something of this sort, this will not satisfy it. For example, good and excellent fit will be 0, but a bad fit will not be 1. It will become a very large number. As it turns out, both these problems can be addressed by what is known as the coefficient of determination. So the solution to these problems is our proposal 2, or this is called the coefficient of determination. Okay. So before we go there, the idea is simple. The idea is scale the residual error based on the simplest model. So the idea is like this. Suppose we have data. So data is scattered like this. Now we have proposed a linear model. Okay, so we are going to propose some model like this. So this is the best model. But we can have the simplest model. The simplest model in this case is simply something like this. What do I mean by the simplest model? The simplest model says y hat is a constant, that is regardless of what the temperature, what the location is. Okay. The temperature is the same, and the temperature is going to be the mean, that is y bar. Okay. So I hope this is clear. So for example, we had several model proposals here. This was the best fit. These two are bad fits, but a really bad fit could be possibly this. So you simply take the average of these temperatures and say that is actually what is going on physically. I have some average temperature and I have some erroneous results, some errors around it. So this is a y equal to y bar, or y hat equal to y bar. This is a constant model or a simple model. Okay, as you can see, it's a very bad model, but nonetheless, it's a model that we can calculate very quickly, and we can say, okay, whatever it is, my error base lies here. Okay, even if I do nothing, I'll get a very, very simple model like this. At least any best fit model, any new model that I'm proposing should be more accurate than this. So if it is only going to perform as well as a constant model, then it's a bad model. So I'll give you a bad score. If it's a really good model, I'll give it a high score. Okay, so let's use that. So now remember, we had this original error, which was sigma y minus y hat square. This we are going to call SR, which is called residual sum of squares. So our proposal one was this itself would be the goodness of fit, but we say, okay, let us compare this with respect to something else. So the comparative quantity that we are going to compare with is what happens with a bad model. With a bad model, you simply have yi minus y bar square. So this is a bad model. This is sometimes called total sum of squares. And as we see, and you will know this much statistics, I assume, but anyway, we will come back to this. This is variance of the base model. And this is variance with the proposed or the best. Yes, this is my fit. This is my base model. Now we can compare SR and ST. Okay, so we can say a measure, a decent measure, a scaled measure of error is SR by ST. But we are going to do one more thing. We will say it is 1 minus SR by ST because, let me come to that quickly, R square, or let me use small r square because we used capital before. Okay. So this R square is known as coefficient of determination. Let's look at its properties. Now, in the worst case scenario, okay, or let's first take the best case scenario. What is the best case scenario? Model fits really well. For example, in our this case, let us say every single point lied on the best fit line. In that case, the error of the actual model SR will be 0. Okay. So this means R square will be 1 minus 0, which is equal to 1. So this is a good fit. Okay. So this satisfies the condition that we had talked about, that you get a good fit in case your error is 0. Now, what happens if it's a bad model? No better than a constant model. What would this mean? This means SR equal to ST. So in this case, R square equal to 1 minus 1, which is 0. So this is a bad model. This condition is also satisfied. Now there is another subtle point here. So let me add that in general, R square will always lie between 0 and 1. We have seen two extremes. The reason is ST is always, sorry, I should say greater. ST is always greater than equal to SR. Now, for a moment, assume that this is true. This would mean that 1 minus SR by ST would always be less than equal to 1. It will always be greater than equal to 0. Because this tells you SR by ST is always going to be less than equal to 1. So this number will always be positive and it will always be less than equal to 1. But why is this true? So I'll try to give you an explanation here. You will need to think a little bit more about what I'm saying, but so why is SR less than equal to ST? Now remember what these two quantities are. ST is sigma yi minus y hat square, and SR is yi minus y hat I square, which is yi minus w0 plus w1 xi the whole square. Now the coefficients for the best fit, these coefficients w0 and w1 were calculated so that SR is minimized over. So remember, we were trying to get the best fit line. So what we were trying to do was to find out what W0 and W1 will minimize SR over all W0 and W1. Okay. But notice that this means if we take the special case, where W0 is y bar and W1 is 0. So if we take one specific line, for example, coming here, when we try to find out the best fit line, what we are saying is, I take this line or this line or this line or indeed even this line. The error of this should be lower than every possible line because that's how we optimize W0 and W1. So one such line over which this has to be better is the straight line which is horizontal. So same thing mathematically, this has to be better. SR has to be better than this line which is W0 equal to y bar and W1 equal to 0, which is this case. This is the same as choosing W0 equal to y bar and W1 equal to 0. So this would mean that SR definitely has to be less than equal to ST, and these are all positive quantities anyway. Okay. So I hope this is clear. The formula for R square, once again, is 1 minus SR over ST, and this is the coefficient of determination. This tells you how good or how bad the fit is, and we'll be reusing this for the next few weeks. Okay, so here is this calculation for our example. So just a simple calculation. Again, I'll leave the calculation to you. I'll just slowly show you these are the results of some calculation and cutting and pasting it from an Excel sheet. Very similar to what we did before, but the calculation works like this. You first need to first calculate W0 and W1 as before. So if you recall from the previous video, we first cataloged X. This is summation of X. Then we cataloged y, summation of y. We also needed x, y, and x square. Okay, so these quantities were needed. Okay, so in order to calculate W0 and W1, and that's what we did right at the beginning. Now, once you do that, you have some expressions. You actually have numbers for W0 and W1. It is only after this, okay, so after this step, you then calculate y hat, which I have called y fit here, for every data point. Okay. Also calculate y bar. Okay, so once summation of y is here, this divided by 6, which is 13.04 approximately, is y bar. We have calculated that. Now we calculate y fit. What is y fit? Y fit is what is y fit? Y fit basically is you go everywhere and calculate y hat, which is y fit, as W0 plus W1x. Since we also already know W0 and W1, you can now see. Okay, so you have now recalculated W0 plus W1x. So x times W1 plus W0 y fit. So you calculate this for these 6 quantities. Once you do that, you square it, y minus y fit square. This is the gap between your prediction and the actual data. You get this. And this is the gap between your data and the average data here. Okay, so you get that too. This quantity now is what we called ST. And this quantity here is what we call SR. Okay. Now, once you calculate that, R square is easy to calculate now. R square is 1 minus SR over ST. In this case, this comes to approximately 0.91 with the numbers here. And you can see this is what we would call a good fit. Okay. Some people prefer above 0.95, but 0.9 and above generally is a decent fit for the data. Okay, so we would have to rethink in case, let's say it is 0.6, 0.5 or something of that sort. We would have to think, maybe I assumed it's a linear model and it's not really a linear model. We'll come to such discussions later on in the course. Okay, so what we have done so far is talk about the goodness of fit and how we can calculate it in this simple case. There is sort of a formal definition for the coefficient of determination. I'll write that down. So this is the proportion of the variance in the dependent variable that can be explained by the regression model. Okay. So what I mean by that is, see, this original figure, there is some noise. Okay. There is some noise in the data, or there is some variance in the data. This data also had some variance when there was really nothing, just a constant. Okay, so if we just put a constant fit here, which was just the mean, then there is some variance there. Now, when you put a model, you should invariably see that some proportion of this variance is actually reduced. So that we call an explanation. So basically, we are able to explain a decent proportion. If all of it was explained, 100% of explained by a model, that means we have got a really good model. But at least we are able to explain 90% of what is happening in this data. okay, which we could not have explained if we had just assumed a mean. So that's what this means physically, the proportion of the variance in the data that we can basically explain simply by the regression model. Now, there are some subtleties here about coefficient of determination versus a correlation coefficient. We will come to this when we come to the probabilistic portions of this course. For now, I'll stop the video here. In the next video, we will look at quadratic models instead of just linear models. Thank you.